Today, we're going to put on our detective hats and dive into a real data-driven mystery. We're going to use a little bit of code and some pretty powerful statistics to hunt for the genetic clues hiding inside two different types of leukemia. So let's get right into it. So here's the big problem we're up against. Just imagine you're looking at a biological sample, and inside it, there are over 3,000 active genes. That is a massive, overwhelming amount of information, right? So the question is, how on earth do you sift through all of that noise to find the handful of genes that are acting differently, the ones that are the key signals for a disease? It's really like trying to find a needle in a haystack full of other needles. To crack this case, we've got a clear 5-step game plan. First, we'll open the case file in a genetic mystery. Then we'll get all our clues organized in preparing the evidence. After that, we bring in our specialist, the SAM detective, before running the analysis. And finally, we'll zero in on our top suspects as we uncover a lead.
Okay, so every investigation starts with a case file, and ours is a pretty famous one in the world of bioinformatics. It's called the Golub Dataset. This is the evidence that holds all the clues we're looking for.
So what's actually in this file? Well, we have what's called gene expression data, which is really just a way to measure how active each gene is. And we have this data for 38 different tumor patients. For every single one of those patients, we know the activity level for 3,051 genes. The real mystery here is, can we use only this data to spot the key differences between two types of leukemia? That's ALL, Acute Lymphoblastic Leukemia, and AML, Acute Myeloid Leukemia.
Now, before any detective can start connecting the dots, they have to get their clues organized. For us, that means we're going to use the programming language R to get this massive data set all cleaned up and ready for inspection. And our prep work breaks down into 4 really clear steps. First, we load our toolkit, then we access the data files, we'll do a quick check on the evidence to make sure everything's there, and finally, we'll group our suspects, in this case, our patient samples. All right, first things first, just like a detective opens up their toolkit before starting an investigation, our first move is to load a specialized package in R called multitest. This thing is great because it contains not only our data set, but also some of the essential statistical tools we're going to need. And what's really cool is just how simple the code is here. The command library multtest is basically us telling R, hey, open the toolkit. Then, Data Golub pulls our specific case file, that Golub dataset, right into our workspace so we can start digging in.
Next up, we got to check our evidence. We run a command called strugolub, which is short for structure, and it gives us this quick summary. The output confirms it. We're looking at a grid of numbers with 3,051 rows, one for each gene, and 38 columns, one for each patient. Perfect! Everything's accounted for. And here's our final prep step, and it's a crucial one. We need to officially label our samples. By using the table command, we see a breakdown of the two groups. We've got 27 patients with ALL leukemia and 11 with AML. So now, our data isn't just a big list of patients anymore, it's 2 distinct groups that we can actually compare against each other. With all our evidence prepped and ready to go, it's time to bring in the specialist. Our lead detective for this case is a really powerful statistical method called SAM. So what exactly is SAM? Well, it stands for Significance Analysis of Microarrays, but you can just think of it as a specialized tool built for this exact kind of problem. Its one and only job is to compare our two groups, the ALL and the AML samples, and flag any of those 3,000+ genes that are behaving in a way that's super unlikely to be just random chance. It is our high-powered gene detector. Now, when you're testing over 3,000 things at the same time, you are bound to get some false alarms. It's kind of like panning for gold, You'll find some real gold nuggets, but you're also going to find a lot of fool's gold, those shiny rocks that look real but are totally worthless. The false discovery rate, or FDR, is how we control for that. It helps us estimate what percentage of our so-called significant genes are probably just fool's gold, so we don't waste time chasing down false leads. All right, the prep work is done. Our detective is on the scene. It's officially time to run the analysis and put SAM to work on our evidence. So the first thing we do is package our gene data and our group labels, the ALL and AML tags, into one single object. Then we feed this neat little package of evidence into the main SAM function. And this is the moment the analysis engine really starts crunching the numbers. And that leads us to a really critical question. How sensitive should we make our gene detector?
I mean, if we set the dial too high, we'll get thousands of significant genes, but most of them will just be noise. But if we set it too low, we might miss the real clues entirely. We have to find that perfect sweet spot. To find that sweet spot, we use something called a delta table. This table shows us how that false discovery rate, our fool's gold rate, changes as we adjust the sensitivity dial, which is called delta. Our goal is an FDR of about 5% or 0.05. And if you look at the table, a delta value of 1.11 hits that target almost perfectly. So that's our setting. So it all comes down to this one number, 1.11. This delta value is the threshold we've decided on. From here on out, any gene that scores higher than this will be flagged by our SAM detective as a person of interest, a potentially significant gene. And this visual really illustrates what SAM is doing under the hood. The analysis gives us a plot that compares our observed results to what we'd expect to see just by random chance. See that straight line in the middle? That represents random noise. But the dots that stray way far away from that line, those are our strongest leads. They represent genes whose behavior is anything but random. Okay, we've run the analysis, we've identified our potential leads. Now it's time for the final stage of the investigation, filtering those results to uncover the most important genetic culprits. We're going to apply one final filter. See, it's not enough for a gene to be statistically significant. We also want it to have a real, meaningful biological impact. So we add one more rule. We're only interested in genes that show at least 100% change in their activity level, what scientists call a twofold change. We're looking for the big players making big moves. And just like that, our investigation is complete. After running SAM with our chosen delta and applying that full change filter, we can finally generate our list of top suspects. This list will show us exactly which genes are significantly more active or upregulated and which are significantly less active or downregulated in one type of leukemia versus the other. And you know, this isn't just some random approach we cooked up. A major scientific study, the MAQCI project, actually confirmed that this two-pronged method, combining statistical significance with the actual size of the change, is the best way to get reliable, reproducible results. We're not just finding clues, or finding clues that other detectives will be able to find again and again. So there you have it. We've successfully used data and code to go from over 3,000 genes down to a focused list of the most likely culprits differentiating these two diseases. And this, of course, leads to the ultimate question. Now that we have this list of solid genetic leads, what's the next step for researchers in turning this fundamental knowledge into an actual treatment, or maybe even a cure? Well, that's where the next investigation begins.